Hello guys, we are going to do Morera's theorem now, which is just the converse of Cauchy's theorem. What this theorem says is, let fz be continuous in a domain D if integral over C fz dz is 0 along every simple closed contour C contained in D, that is your domain, then fz is analytic in D. We have given two things. First is the function is continuous and its integration is 0 along this closed contour C. So for this we have to fix the point z0 first in the closed contour which is contained in the domain, and we have to prove that this function is analytic in D. So I have fixed a point z0 inside this closed contour C and taken another point z and a small h enough which is positively small so that the line segment connecting z to z plus h is also inside this domain D. So first of all we have to start with, we have fixed z0 in D and we have defined a function fz, the value for which is equal to integration from. Now we start our integration. What is our initial point z0 and the final point I have taken z, f of t dt. Now what does this mean? If the integral depends upon the initial and final point or initial or terminating point, then this integral is independent of the path followed, right? So this fz is, because we have fixed z0, so integral depends upon the initial and terminal point, so this integral is this integral is independent of the path of integration. From z0 to z inside D. Fine. Next, now what we have to do is I have chosen a small h in absolute value so that this line segment z to z plus h lies inside D. So small h I have chosen. So choose h small enough in absolute value so that the line segment from z to z plus h lies inside the domain. Now consider sorry, f of z plus h minus f of z over h. This thing is equal to, now see, 1 over h. What is f of z plus h? What we have taken fz to be equal to integration from z0 to z ft dt. What is the terminal point? The point on which this f depends, right? And the initial point should be z0. So if here it is z, then the terminal point is z. So similarly in this case, if here it is z plus h, then initial point is z0 obvious and the terminal point should be z plus h for the first function. So this is f of t dt minus this integration from z0 to this z ft dt, right? Next, I need to change the sign now. See how this sign is changed. If I interchange the limits, then this negative sign changes to the positive one. So I'm writing this first. Instead of z0 to z, I should write from z to z0 ft dt, and the sign changes, plus integration from z0 to z plus h ft dt. Very fine. Which is equal to 1 over h collectively. Now z to z0 and z0 to z plus h. So this is z to z plus h ft dt. Clear? Okay, now what I have to do now, I just subtract f of z on both the side, small f of z. Okay, let's subtract, taking the mod of f of z plus h minus f of z over h minus f of z. I am subtracting this, which is equal to mod of 1 over h integration from z to z plus h. This is f of t dt, and subtracting fz. Next step is very clearly, just say this 1 over h. I'm taking fz inside the bracket with f of t minus f of z. Now how this happens? If you solve the bracket, if you solve the second term with 1 over h, see what this will become. 1 over h integration from z to z plus h. Skip first one, let's check the second one, f of z dt. Since the integration depends upon t, so fz can become outside. So this is f of z over h integration from z to z plus h dt. This is equal to f of z over h, and this is h. So this cancelled out, we are left with fz. That is what is written over here. So when you solve this, you will get back to your previous equation. So we can take fz inside the bracket. Alright, now next, because it is given that function is continuous, can I apply the definition for the continuity? See, as by the continuity of f of z for every positive epsilon, we have this function, that is mod of f of t minus f of z less than epsilon, right? Taking mod of h sufficiently small. So I'm writing now this thing. What is this equal to? Now this can be less than equal to 1 over mod of h and integration from z to z plus h. This is mod of f of t minus f of z and mod of dt. So this is further less than equal to 1 over mod h integration from z to z plus h. This is nothing but your epsilon and mod of dt. So this is equal to 1 over mod h. Epsilon is outside, and when you solve that integration, we have left with, what is the value for this integration? H mod h. Fine. but now they cancelled out and we will left with epsilon only. So thus mod of f of z plus h minus f of z over h minus f of z, this mod is less than epsilon, but epsilon was arbitrary. So therefore limit h tends to 0, f of z plus h minus f of z over h, this is equal to f of z, and this is nothing but your definition for differentiability. So which is equal to, which implies this is f dash z is equal to fz. So thus if this thing happens, your fz is analytic in D with f dash z is equal to fz. So f of z is analytic in D with f dash z is equal to fz. Now whenever your function is analytic and having the first derivative, then by Cauchy's integral formula we are having the result that this fz must have derivative of all the orders, right? So moreover, by Cauchy's integral formula, fz must have derivatives of all orders. That means if f dash z is equal to fz, then we are also having f double dash z is equal to f dash z, then f triple dash, that is the third derivative, is equal to second derivative of fz. That means our fz is having now derivatives of all orders, right, with this fz. So thus this f dash z exists at all the points in D, right? So from this we can say that this f dash z exists at all the points in D, and whenever your derivative exists at all the points in D, we say that that function is analytic. This is only the definition for analyticity. So hence and hence fz is analytic in D. Fine? Alright. Next is just a corollary for this. Let fz be analytic in a simply connected domain D. Now it is given that your function is analytic. In Morera's theorem, we have to prove that this function is analytic if it is continuous. What is given in Morera's theorem? The continuous function is given and integration fz dz equal to 0 is given. From that we have proved our function to be analytic. Now here it is given that this function is analytic in a simply connected domain D, and if z0 is a point in D, then fz is equal to, which is given, z to z ft dt is analytic in D. We have to prove that this function is analytic. Just now we have proved that this fz is analytic. How we have proved? We have taken the function to be continuous. Now whenever a function is analytic, obviously this function is continuous, right? And from this analyticity we can get integration of fz dz is equal to 0 by Cauchy's theorem, right? So whenever a function is analytic, and if we are having a point z0 inside the closed contour C, we can use the Cauchy's theorem and by using that theorem we can get integration fz dz is equal to 0, and then the same proof what we have done in the Morera's theorem. Let's start. Now since it is given that fz is analytic in a simply connected domain. Now see, it is very important that your domain should be simply connected, because if domain is not simply connected, then that integration cannot be equal to 0. We have to take our domain to be simply connected, right? So whenever a function is analytic in a simply connected domain, D, what will happen? Our integration for fz dz is 0. This is what the Cauchy's theorem says, and Morera is just the converse of the Cauchy's theorem. So if your domain is not simply connected, then this may not happen. This need not be 0. So it is given that domain is simply connected, we write this thing is equal to 0 along every closed contour C contained in D. Thus the value of the function, this fz. This fz is independent of the path of integration from z0 to z inside D. See, from z0 to z. Right, because z0 is a fixed point in this contour. Again, the same proof is now, choose z small enough in absolute value so that line segment joining z to z plus h is contained in D, right? So then we consider this function f of z plus h minus fz over h, and we solve this. Then we subtract fz from both the sides, and then we'll get epsilon by using the definition of continuity of fz, and then this whole thing is equal to f of z, and this is nothing but the first derivative of capital F of z. So thus fz is differentiable in D and hence is analytic in D, right? The same proof. Now there is a remark, a very important thing. Now if fz is analytic in a domain D, we are not guaranteed that this integration fz dz is equal to 0. What I have said earlier, along every simple closed contour C contained in D, it is not guaranteed that this thing is equal to 0. What is the requirement for this integration to be 0? The requirement is we need simply connected domain. We must have a simply connected domain. Let's check over an example. Suppose we are having a function f of z is equal to 1 over z. Suppose we are having this function, right? And let's draw the domain. Now where this function is analytic? First tell me where this function is not analytic. You are having 1 by z, that means this function is not analytic at origin, z equal to 0, because if z is 0 then this function is not defined. So this function is not analytic at z equal to 0. If I write 1 over z minus 1, then this function is not analytic at z equal to 1. So I take this origin. The function is not analytic at this origin. So I must draw a circle. Suppose I have drawn a circle having the radius, any radius. Suppose I am taking this circle to be having the radius 1 by 2, and one more circle I am drawing having the radius, let's say 2. Right? Since the function is not analytic at 0. So where the function is now analytic? In this annulus, right? In this annulus, function is analytic, bounded by the two circles mod z equal to half and mod z is equal to 2. So between these two circles, the region, yellow shaded region, the function is analytic over here. So here the function is analytic. In this annulus, right? And this is your domain, this is your domain D. Now what is the value of this function now? Let's draw one more circle. Suppose is the domain is simply connected? No, it is now multiply connected. This is the origin where the function is not analytic. This is your first inner circle having the radius 1/2, and this is your outer circle having the radius 2. I'm making a new circle having the radius 1. The blue colored one mod z is equal to 1. Now see this circle where the function is analytic. If we consider only this circle, suppose our function is on this circle, mod z equal to 1, f of z dz. What is the value for this function over this circle? See, function is analytic between this annulus, right? That is this yellow colored region. So if we consider this blue circle, then half of the portion or sum of the portion of this circle, the yellow shaded one, here the function is analytic, right? Here the function is analytic. What we say about the inner part of the circle, the pink colored one, the interior, now this yellow colored one is contained in the domain D because here the function is analytic. But what about this pink colored portion? Here the function is not analytic. So this pink colored portion is not included in your domain, right? Because in domain the area existed where the function is analytic. So the yellow colored portion is in your domain, but this inner portion of the circle mod z equal to 1, that is the pink one shaded region, here the function is not analytic, so this portion is not included in your domain. Hence, this integration for mod z is equal to 1 cannot be equal to 0. This integration is not 0, right? Because now your domain is not simply connected. So what is the value for this function then? This is 2 pi iota only, right? So whenever your point is inside the closed contour C and the function is analytic in simply connected domain, then only the integration for fz dz is 0. But if the domain is not simply connected, that is this interior is not contained in the domain because here the function is not analytic, then this integration is need not be equal to 0, right? So this is just a small concept. So next time we are going to do the Cauchy's inequality and Leibniz theorem, and do subscribe my channel for the latest videos. And one more thing is that if you need my course Real Analysis, you check the description box. The link is given for that course. Just check over it. And thank you for watching this video. Goodbye. Have a nice day.